Hi, hello friends. Welcome to T Academy. Let's continue the previous assistant engineer electrical question paper discussion here. In my previous videos, I already covered uh, electrical circuits and control systems. Now I am going to discuss the electrical machines. Okay, so in this video, we are going to cover 10 questions which are asked in the DC machines and as well as AC machines here. Okay, so the first question here it is, as you see, a 5 kVA single phase 50 Hz transformer has 50 watts iron losses, 150 watts full load copper losses. Its efficiency at full load 0.8 power factor lagging will be approximately. So friends, observe here, this is a question paper asked in the AE examination, but it requires some of you requires calculator, but in the examination the calculator is not allowed. So you have to be good at your problem solvings and mathematical equation solvings. You should be good at this skill here. Now here they given a transformer, they given a losses, they given a power factor, and they given the rating. So just you need to substitute all these values into the formula so that I will get the answer here. That's it. So what is the efficiency of the transformer? Efficiency of the transformer is equal to, so output kVA. So output kVA into power factor divided by, so output kVA into power factor plus the losses. We have iron losses plus we have copper losses. That's it. So this is the formula here. So you know all the values here, just substitute and you'll get the answer. So here the examiner is going to test your mathematical solving capability. That's it. So output kVA is what, you know, that is a 5. So 5 kVA into, I will say, 10 power 3 into power factor is 0.8 divided by, so 5 into 10 power 3 into 0.8 plus what are the iron losses we have? So we have 50 watts of iron losses plus we have 150 watts of copper losses. Okay, so simply if you are solving this, you will get the efficiency of 95% here. So answer will be D here. So D is the right answer for this question here. Okay, next one. So this question is asked in the transformers. There is a Scott connection of transformer here. Okay, so in a T connection, the percentage tappings. Okay, the percentage tapping of main transformer and the tracer transformer respectively. So here the examiner is asking you whether you know the Scott connection transformer and what are the tappings are there. So to understand this, just have the diagram of this Scott connection or T to T transformer. So generally it is used to convert three-phase supply to two-phase supply or two-phase supply to three-phase supply. Vice versa, we can do here. So this is the advantage of this T to T connection. Now here we have the transformer here. Let me draw the transformer diagram here like this. So primary and secondary windings, and here we have one winding here like this. Okay, and here we have, so let me erase this one. So I'll retry it again. Okay, so let me correct here. So Scott connection of transformers. So let's draw the Scott connection here. Here, okay, let me change here, right? So here we have the teaser transformer winding here like this. Okay, and here we have main transformer like this. Okay, and here we have the secondary winding of this transformer, and here we going to connect a load here. So this is a load. Okay, and here we have phase A and phase B. So this is the main transformer like this, and again here we have the another transformer winding here which is connected to B phase like this. Okay, and here we are going to connect another load here. Okay, so this is a ABC phase here, and here we have R and Y, and here we have B phases. Okay, just I'm doing the rough diagram here. Now, so this is our teaser transformer here. Understand here? This is our teaser transformer, and this will be our main transformer. So this will have, so 0.5 times that of NP. That is a primary winding. That is a 0.5 times that of NP. And here here we are going to make a tapping here. That tapping will be root 3 by 2 times that of the NP here. That's a primary winding here, and here we have a NS secondary winding, and here we have secondary winding. So what I mean to say here it is, so the simple thing is, here we have in Scott connection there are two transformers. The transformer one is a teaser transformer, the second one is a main transformer. So main transformer we're having a 50%, that's a 0.5 means 50% of this primary winding, and teaser transformer is having a tapping of root 3 by 2, that is nothing but 86.6% of the winding here. So in the given question, the percentage tappings of the main transformer and teaser transformer. So what's the main transformer? Main transformer is 50%. Okay, 0.5 is 50%. Teaser transformer is what? 86.6% here. Okay, remember here they may interchange this transformers here. So they will ask tapping of teaser transformer to and main transformer, like that they ask. So for a main transformer it's a 50% or 0.5, and this will be 0.866. So answer is, you know that it's a 50 and 86.6%. So answer is A here. Hope you understand this question. Okay, and I will move to the next question here. Next one. So this question is asked in the DC machines here. A 220 volt DC shunt motor with armature resistance of 2 ohms is running at 1000 rpm, draws a current of 10 amperes from supply. It is braked by plugging. The braking current will be. So simple, see here. What's the meaning of plugging here, sir? So plugging means here we have a DC shunt motor like this. Okay, I'm just drawing the rough diagram here. This is DC shunt motor, and it is having a voltage of what? 220 volts, and its current will be what? Having armature resistance of 2 ohms. Okay, and running at 1000 rpm draws a current of 10 amperes from supply. So this is the current from drawing from 10 amperes from supply here. It is breakaway plugging means what is happening is we are interchanging the terminals here. Okay, so at the time what will happen is generally the current formula is I is equal to V minus EB by RA. This is a basic formula here, you know that. But in case of plugging, what will happen is we are going to interchange, so that the here it will be V plus EB. Okay, so V plus EB. Okay, so V plus EB by RA. First of all, what is EB? So EB you need to calculate here. So before plugging, what is the value of EB? EB is equal to V minus IA into RA. So V is nothing but 220 volts minus IA is what? IA is at 10 amperes and resistance of this is 2 ohms. So simply it's going to be 200 volts. Now this is the current. So this is a breaked current, or IB I can say. So IB, breaking current, is equal to, so V is 220 plus 200 divided by resistance is 2 ohms. Now it is nothing but 420 by 2. The answer will be 210 amperes answer. So answer is for this question will be what? It is B here. Okay. So B is our right answer, 210 amperes. Next question. Yeah, this one is. So very simple question asked from the three-phase induction motors. So three-phase induction motor has a standstill rotor impedance. So standstill means when the motor is at not rotating condition. So it is 1 plus J 4.3 ohms per phase. Okay. Now to get the maximum torque at the starting, the resistance per phase required to be connected in series with the rotor here. The basic condition is at a standstill condition slip is nothing but 1. To get a maximum torque means the slip should be is equal to R2 by X2 is equal to S. Now we know that we need some extra resistance. So R2 plus R extra resistance, okay, is equal to slip is 1, you know that, so it is going to be equal to X2. Now I want Rx value is nothing but X2 is what here from this impedance of Z is nothing but R plus Jx type. Okay, it is nothing but 1 plus 4.3 J here. So X2 value is 1 point, sorry, I'll correct here. So Rx from this formula is equal to X2 value is 4.3. So 4.3 minus R2 value is 1. So it is nothing but 3.3 ohms here. So answer is for this question will be, it is 3.3 ohms that must be connected in series with the rotor to get a maximum torque condition here. So the answer is 3.3 ohms. So we'll move to the next question. The load characteristics of alternator will have drooping shape due to. So first of all, what is this load characteristics. So load characteristics will tell you the relationship between the terminal voltage of the alternator to the load current IA here. Okay, so it gives a relationship between terminal voltage and IA here. If you have seen the relationship here in the given question, so here we have armature current or load current, here we have voltage, and here we have, okay, so EB is a voltage or E is a voltage, EG is a voltage here. Now for leading power factor, the graph will be like this. Okay, for unity power factor, graph will be, so this will be for leading power factor, and this will be so unity power factor, and here we have something like this, it is lagging power factor. So these are the diagrams. So the load characteristics of alternator will have a drooping, that means is it going to be decreases like this. Why it is decreasing like this? There is a question here. So it is going to decreases like this, no? So why it is like this? There is a question here. Now we know that the V phase or E phase or EG is equal to, let me take VT here, not VT. Okay, so VT is equal to EMF generated EG minus it is IA into ZS. What is ZS? It is nothing but synchronous impedance. So synchronous impedance. So as a synchronous impedance is there, what is the meaning of synchronous impedance? So it is having armature resistance plus J into XS. So armature resistance, this one is armature resistance, and this one is synchronous reactance. Sorry, synchronous reactance here. So this is a synchronous reactance and this will be armature resistance. Okay, so the droop is because as the current value increases, okay, so as the current value increases, what about this entire drop? It's going to be decreases the phase voltage. That means because of the current increases, the impedance, the voltage drop will be increases here. So the internal voltage drop because of resistance and synchronous reactance. Okay, it's a synchronous reactance here. Okay, so I'll repeat the question again. The load characteristics of alternator will have a drooping shape due to the impedance of this machine. That impedance consisting of resistance and reactance. Simple. Next question. The torque developed by split phase motor is proportional to. So simple question. So torque developed by split phase motor is because of sine of angle between the main flux and auxiliary flux. Okay, so it is angle between these two values. So sine of angle between Im and Is, Im and Is here. So answer will be A for this question here. Okay, so we will maintain this angle between two fluxes as 90 degrees to get a maximum amount of torque. Okay, so this point is very clear. So in case of DC machines, the angle between the main flux and armature flux is 90 degrees, so that you will get a maximum torque in case of a DC series motor especially. Okay, next one. This question is from the DC machines, right? So numerical type, a 240 volts DC series motor, so it should be motor here. So motor takes 40 amps when giving its rated output 1500 rpm. Its resistance is 0.3 ohms. The value of resistance which must be added to obtain the rated torque at 1000 rpm. So here the condition is you must get the rated torque. That means the torque should be remain same. Okay, so there are two conditions are given. So first we'll draw the circuit here. So there is a field winding and we have here armature like this. Now it carrying a current of what, 40 amperes, and it having a voltage of 220 volts, 240 volts like this. Okay, so 240 volts is there. Now it's rotating at a speed of 1500 rpm. Now what is the back EMF? First of all, first case, let me take EB1 is nothing but V minus IA into RA. So V is what, 240 minus IA is 40 amperes, resistance is what, 0.3. So it's nothing but 228 volts here. So 228 volts is a here. Now rated torque means same, and here in the given condition the current will also will be same. So I can say that EB by EB1 by N1 is equal to EB2 by N2. We know that EB1 value, N1 value, and we don't know EB2 value. We are going to calculate, and N2 value we know. So EB2 is equal to back EMF 1 228 Okay, so into N2 means this one value will be N2 and this one value will be N1. So N2 means it is going to be 1000 divided by N1 means it is 1500 RPM. So if you solve this, you will get an answer of 152 volts here. Now this is the back EMF in the second case. Now what will be the extra resistance added so that you will get the rated torque at 1000 RPM. So torque remains to be same. Now first we know that EB2 is equal to V minus IA into RA. Okay, so V remains same as it is. It's nothing but 240 minus current also remains same 40. Now here RA is, we know RA plus some R external resistance we are going to add. Okay, so this value we need to calculate. So EB2, you know what is the 152 volts. So 152 is equal to 240 minus 40 into 0.3 plus RET external resistance. So if you solve this equation here, you'll get the R external resistance as 1.9. I'll write here. So 1.9 ohms is the answer here. So answer for this question will be 1.9 ohms. That means if you are adding 1.9 ohms of resistance in the circuit, you'll get the same torque here. Next question. So this question is from the synchronous machines, right? Synchronous machines. Now here, from the following three statements, which of them are give correct? So you need to choose the correct options here. So first of all, V curves of the synchronous motor gives location between the armature current and the power inputs for different field currents. So that is a wrong statement. Why? Because V curves gives a relationship between the armature current and field current. Okay, but not gives a relationship between the power inputs here. Okay, so V curves will discuss about armature current and field current, and armature current with respect to field current with respect to power factor. So these two are the parameters here with respect to field current. We have seen this over excitation, under excitation, normal excitation. You have seen this, right? So V curves you have discussed. So this is the wrong statement here. Next one. In a three-phase alternator, the ratio of phasor sum of the induced EMF per coil to the arithmetic sum of the induced EMF per coil is known as a coil pitch factor. Okay, so here the EMF, this statement is correct here. In case of three-phase alternator, the ratio of the phasor sum of the induced EMFs per coil to the arithmetic sum of the induced EMF per coil is nothing but coil pitch factor. It can also be written as the EMF produced when the coil is short pitched by resultant EMF when the coil is full pitched. So I'll write the formula here. So coil pitch factor is nothing but, so resultant EMF when the coil is short pitched divided by resultant EMF ER when the winding is full pitched. Okay, that is nothing but coil pitch factor. So this statement is correct here. Next one, when the transformer is on no load, the induced EMF in the primary and secondary windings will be, so when the windings in phase with the main flux. See here, when the transformer is on no load condition, the induced EMF is in primary and secondary windings is in phase with the main flux. You have seen that the basic diagram of this induced EMF here. Here we have phi, and here we have induced EMF E1, and here we have induced EMF E2 here. Okay, so they will have a angle of 90 degrees with respect to flux here. Between E1 and E2 there will be 180 degrees. So E1 and E2 means there should be 180 degrees here, but in case of E1 with the main flux is 90 degrees. So this statement is also wrong here. So only the statement B, second one is a true, and 1 and 3 are false. So option A will be the correct answer for this question here. Okay, so we'll move to the next question here. So this question is from the three-phase induction machines. A three-phase induction motor has a short circuit current which is 3 times of its full load current. Okay, its full load slip is 4%. The ratio, the ratio of starting torque to the full load torque when it is started with a star delta starter is. So in case of a three-phase induction motor, the full load slip is 4% and short circuit current is 3 times that of its full load current. At that time, what we need to do, we need to calculate the ratio of starting torque to the full load torque when started with a star delta starter here. So options are 1.5, 1.2, 2.1 and 0.12 here. So first we'll take the slip here. So slip S is equal to, it is 0.04, nothing but 4%. Okay, 0.04 will take. Now we'll take the formula. TST, starting torque to the full load torque, to TFL is equal to, so current IST by IFL full load square into S into FL. So full load slip. Okay. So which is equal to, so here we have 1 by 3 here. So it's nothing but 1 by 3. And the ratio of this starting at full load torque is, we know that it's 3 times. So 3 square into SFL is 0.04. So which is equal to 0.12. Okay, the ratio of the starting torque to full load torque is 0.12. So D will be the right answer for this question here. And the next question here, it is a single phase squirrel cage induction motor is designed with two windings in the stator with a displacement of 90 degrees, 90 degree electrical. The currents fed to these windings should have a displacement of, so the currents fed to these windings have a displacement of 90 degrees electrical. So answer for this question will be C is the right answer for this question here. So that's it for this session. Now we'll continue the previous AE electrical paper questions in the next upcoming videos. Thank you friends. Have a nice day. If you like this video, please share with your friends and give respect to our efforts. Thank you. Have a nice day.